So for this lecture, we will discuss what are complete measure spaces and how to complete such a measure space if they are not complete. In particular, we will talk about uh, the completion of a measure space and later connect what is or what are the Karatedori and Han-Kolmogorov extensions in connection to complete measure spaces. So let's start with the following definitions. So suppose you have a sigma algebra. So X is a set, sigma is a sigma algebra, and mu is a measure. So a subset A of X is said to be mu null if the measure is 0. So in this case, null sets with respect to a measure are not necessarily empty. So there are, for instance, in the case of the Lebesgue measure space, all countable sets are null sets with respect to the Lebesgue measure. And this measure space will be called complete if the following conditions are satisfied. So take a measurable set that is mu null, then any subset must be also measurable. Again, a measure space is said to be complete if every null sets of if every subset of a null set is again measurable. And in particular, this implies that so in this case, A is also mu null. Okay, so I need to emphasize here, of course, A must be in sigma so that we can apply mu. Example, the Lebesgue measure space is complete, whereas the Lebesgue-Borel measure space is not. So the first statement, that is the completeness of the Lebesgue measure space, comes from the fact that the Karatedori extension measure space is in fact complete. And for the second statement, again, using the Cantor set, which is measurable, there are subsets of the Cantor sets that are not measurable, Lebesgue measurable, and in fact not Borel. So the Lebesgue-Borel measure space is not complete. So for this first statement, as I said, this comes from the fact that the Karatedori extension that is the set X, the set of measurable subsets in the Karatedori sense of a pre-measure space, say X R mu, R is a ring. So here the measure is the restriction of the outer measure to the measurable sets is complete. Well, the proof is in fact straightforward. If you take a measurable set with a measure 0, outer measure 0, well, that is the same as this restriction measure. And you take a subset of n, then by monotonicity, of your outer measure, the outer measure of A must be also 0. Hence, A is measurable as well, since we already established that sets having outer measure 0 are measurable. And that is a completeness. Any subset of a mu null set with respect to this measure is again mu null. Okay, so we said that here that in order for a measure space to be complete, we need the fact that all subsets of null sets must be also null. The question is, what if this is not the case? Then we can construct the so-called completion. And this is done in the following theorem. Suppose I have a measure space. And let us denote by script n the set of all subsets of mu null sets. So we collect all subsets of mu null sets and define sigma bar to be a sigma union n. In other words, this is the union. This is the collection of all unions A, B, where A is in sigma and B is a subset of a null set. So the first step is to enlarge, your sigma algebra by combining all subsets of null sets. And in fact, this collection, the resulting collection, is a sigma algebra. And one can find, and in fact, a unique measure, say mu bar, from this new sigma algebra with the following property. So such that mu bar is equal to mu on sigma. In other words, the restriction of your mu bar is equal to mu. Okay, and if this is a measure, then we have this measure space, and this is complete. And in particular, take note that this is, or let's say in particular, if your original or your given measure space is sigma finite, then it follows easily that this new measure space, this complete measure space, is also sigma finite. Okay, so this is this complete measure space is what we call the completion of your given measure space X sigma mu. So again, given a measure space X sigma mu, you denote by script n the subsets of null sets. Okay, and then you combine You take the union of measurable sets in sigma and subsets of null sets B in N. You form this new collection sigma bar. And from this theorem states that this is a sigma algebra. So we need to establish 4 things. Namely, first, that this is indeed a sigma algebra. Second, the extension of the existence of the extension. Third, its uniqueness. And fourth, its completeness. The completeness of the resulting completion. So put in other words, to complete a measure space, you just modify your sigma algebra by enlarging it, combining all combining all subsets of null sets, okay, and then you extend your measure. So let's start with the proof. And as a first step, we wish to establish that this is a sigma algebra. Okay. Now, take note that by definition, or note that the empty set is in sigma, because this is a sigma algebra. And the empty set is also in N. Namely, this is the subset of itself, okay? And the empty set is mu null, okay? With the definition of a measure. And this implies immediately that your sigma algebra and the null sets are subsets of your sigma bar. Well, to see this, it is enough to take, let's say, if you take A to be empty, then you get an element N in N. And if you take B to be empty, you get an element of sigma. Okay, so from the definition, sigma bar contains the original sigma algebra, and it contains the set script N. Okay, so to show that the empty set is in N, as I said, you just take B equal to N equal to the null set. Okay. Sigma algebra. So we need to establish the following. I want to show that X must be in sigma bar. Okay. The goal is to write this as a union. One, an element of sigma, and the other, an element of N. Well, you can simply write X as X union empty, and take note that empty is in N. The empty set is in N. Therefore, this implies that X is in sigma bar. Again, recall that in order for you to be an element of sigma bar, you must be a union of 2 elements or 2 sets, one in sigma and one in N. Okay, so that's what we have established here. Okay, so here let us consider the following assumption, and since this will be utilized in several parts, let us name that. or let us highlight that one. If A bar in sigma bar, if and only if, okay, so A bar is equal to A union B. A is in, okay, for some A n in sigma, okay, or let us say with B subset of n for some AB or AN in sigma. Okay, so let us highlight this because this will be repeated several times. So for convenience, let us name this as, let's say, star. Okay. So let A bar be in sigma bar. Okay, then we wish to write the complement of A bar in the same manner. So if we would like to see if this is indeed in sigma bar, we need to write this as the union of two elements, one in sigma and one in n. Okay. So to illustrate the situation of star, this one inside the box, let us say this is our set X. And then you have an A bar. So A bar is the union of two sets, A, which is in sigma, and B, which is a subset of N. Okay, so let's say this is N. It contains B. Okay, so this N is also in sigma. And these two parts here is A bar. So A bar is the union of B and A. Okay, so let us highlight that one. So this would be your A bar. And we need to look at the complement. This one. So the complement is basically the region outside this green part. And okay, that is the same as, so if you take the complement, let's say, of the union, but not with B, but with N. So you can divide the complement into two parts. The first part would be this region, the region being highlighted right now. Okay, and that would be what? A union N complement. And this other region here, let's say, let's change the color. this one. And this is basically what? This is n, but you remove the green parts. So this is basically n minus a bar. So we have written the complement of a bar as two sets. One, that is n minus union a bar, n minus a bar, and the other that is the complement of the union of C. Okay. Take note that, okay, if you have this representation here, a bar as union A union B, A and N are in sigma, therefore the union, and hence the complement of the union is in sigma, because this is a sigma algebra. Okay, and the other one, so let us write that here, since a n is in sigma. Here, since this is a subset of course, this is a subset of n, obviously, and n is mu null. Okay. We need to add here that n must be mu null. So that's the case where if a bar is in sigma bar, then the complement is also in sigma bar. And finally, for countable closure under countable unions, let us take a sequence in sigma bar for each n, a positive integer, so that I can write this as what? The same as before, an bar is an union bn, where an is in, let's start with bn. Bn is a subset of n sub n. Mu of n sub n is 0. A sub n and n sub n are in sigma. So this is basically your definition of a sigma bar. So we would like to look at the union of an bars. And again, to verify that this is in sigma, it is enough to write this again as a union of two elements, one in sigma and one in n. Well, from this equation, we can split the union into two parts. The union of the a sub n's and the union of the b sub n's. Okay, since a sub n is in sigma, therefore the union of those sets are in sigma, because we have a sigma algebra. The other one, we need to verify that this is indeed in n. But note that the union of the b sub n's, since each b sub n is contained in n sub n, then this is a subset of n sub n. Again, n sub n is in sigma, so this is in sigma. And by monotonicity, and subadditivity, sigma subadditivity of mu, you get that the outer measure, or the measure, I should say, of this is 0. And you can simply establish this using sigma subadditivity and monotonicity. Okay. Or I should say, I think sigma's subadditivity is enough. Okay. And so let us put this above. Okay, so we have written the union of the a sub n's by a union of two elements, one in sigma and one in n. Therefore, this is in sigma bar. Okay, so that's the proof of sigma bar being a sigma algebra. Okay. Step 2, existence of your measure, extended measure. Okay, so let us highlight this one. One way is, of course, to construct. So we define this function as follows. So mu bar, a bar to be mu of a, with star. Okay, and what is this star? This one here. So if you have an a bar and sigma bar, you write it as a union of two elements, one in sigma and one in b. Okay, so in this case, the value of a bar with respect to mu bar is just the measure of a. So here we neglect b. Since b is a subset of a null set, roughly speaking, it will not contribute to the measure, so we can ignore that one. And this is well defined because a is in sigma. So the right-hand side makes sense. Now, of course, we still need to show that the definition of mu bar is independent of the representation as union of elements for a bar. In other words, if a bar can be represented also in this way with primes, okay? So with b prime being a subset of n prime, and the measure of n prime is 0, and a prime n prime is in sigma. Then the value of a bar is also a prime. Okay, so this means that if you have another representation of a bar as a union of two elements, a prime in sigma and b prime a subset of a null set, then you can use this representation to calculate mu bar. In other words, you just take the measure of a prime with respect to mu. Okay, to see this, so indeed, Take note that A being a subset of A bar is equal to A prime union B prime, but B prime is smaller than N prime, or a subset of N prime. Okay, so from this, we have applying monotonicity and subadditivity of a measure. So measure of A is less or equal to the measure of A prime union N prime due to this inclusion. And this is equal less than or equal to the sum of the measures. But then this is equal to 0. Hence, this is equal to mu A prime. Okay. Aha. So I think I need to replace this by mu of A. Okay. So the measures is the same. So that's one inequality already. Mu A is less than or equal to mu A prime. Well, you can interchange the roles. So by symmetry of argument. So similarly from, okay, let's start with A prime. A prime is a subset of A bar, but A bar is A union B. But B is a subset of N. So from this, we also get that the measure of A prime less than or equal to the measure of the union of A and N by monotonicity, applying subadditivity, and recognizing that the measure of N is 0, you have the reverse inequality. Okay, so mu bar is well defined. Again, it does not depend on the representation of A bar. So if you have another representation, then you can use that as well, and you will get the same result. Okay, so that's the first part. Well, the fact that mu bar is well defined. Next, of course, we need to show that mu bar restricted to sigma is mu. In other words, mu bar A is equal to mu of A for any A in sigma. Indeed, mu bar A. Okay, take note that this is, we have established a while ago, this is a subset of sigma bar. I can write this as A union the empty set. And this is in sigma, this is in N. According to the definition of mu bar, you just take the measure under mu with respect to mu of the element in sigma, and that is A. So yeah, mu bar restricted to sigma is equal to mu. Okay. And finally, we need to verify that this is indeed a measure. Okay, so if we take, for instance, this set empty, well, we can write this as what? or from this part here. Let us call this double asterisk. Since the empty set is in sigma, okay, so mu bar of the empty set is the same as mu of empty, and since mu is a measure, you have this. It is equal to 0. Okay. So probably you want also to emphasize that mu is a measure. So that mu, the empty set is 0. Okay, let an bar a countable sequence, and it is pairwise disjoint with the representations as in the first step, step 1. By these representations, I mean precisely this part here. Okay, and from this step, we have written the union of A bar n in this way. So if that is the case, then if we take mu bar of the union of the A bar n, so this is equal to the union of an union with the b sub n's. Again, to emphasize, this is in sigma, this is in n, and based on this representation, according to the definition of mu bar, we can ignore this part and take the measure of mu of the union of a sub n from 1 to infinity. Now, we can apply the additivity of mu, sigma additivity. And take note that an is in, or a subset of an bar. Hence, if the larger collection is pairwise disjoint, then it follows that this one is also pairwise disjoint. Okay. Hence, sigma additivity of mu can be applied. And now, what? You have the fact that mu bar and mu coincide with mu on sigma. Okay, since an is in sigma, then you can do this. So the values, or mu and mu bar, are the same. Okay. Or we could go directly to this equation. Since an, recall from step 1, an bar was written in this form with an in sigma and bn in n. Okay, so again, to take the value of a bar n with respect to mu bar, we can neglect this and just take the measure with respect to mu of an. So that follows from the definition in fact of mu bar. And that's it. The what mu bar of the pairwise disjoint union is the sum of the mu bars. So therefore, mu bar is a measure. Now, if we go to the next step, and that is uniqueness of the extension. So standard way establishing uniqueness, you take let's say two extensions, and then you wish to show that they are equal. So let us consider a measure space such that nu is equal to mu on sigma. Suppose you have another extension. Now, for any a bar in sigma bar, we have the following. So let's start with the measure with respect to nu. Okay. Here we again use the representation star as above. So what this is equal to nu of A union B. A is in sigma, B is a subset of a null set. Monotonicity of a measure implies this one. Now, take note that this is what? An element of sigma. And this implies that this one is continuing the equality here according to this assumption here. So nu and mu are the same on sigma. Okay. Next, this is less than or equal to mu of A by subadditivity plus mu of n. But of course, we can neglect this because this is 0. And again, this is equal to mu of A with the same reasoning because A here belongs to sigma. Okay, so mu of A is the same as nu of A. Now, you apply monotonicity once again. This is equal less than okay, since A is contained in A bar. Okay, so you end up with what? You started with this quantity. You have this. Okay, I think we need one more step. Or at least a remark. Take note that by definition, this is mu bar A bar. Okay, so mu bar A bar is greater than or equal to this, but less than or equal to this quantity. Hence, they must be equal. In other words, all of this must be equalities. Hence, mu a bar, mu bar a bar is the same as nu of a bar. Since this is true for any a bar in sigma bar, this means that mu bar is the same as nu. So therefore, if you have another measure space that extends mu on sigma bar, then it must be the same as your mu bar a while ago. And finally, to prove completeness of the resulting measure space or the constructed measure space, and this will be our final step in this theorem. So let's start with what? Let's start with a mu bar null set. Okay, let us just recall the definition. That is a bar is in sigma bar, and the measure with respect to mu bar is 0. Okay, that is basically the definition of mu bar null set. And you take a subset, let's say a C bar of n bar. I should say a bar. Okay. Well, we would like to show that this subset of the null set is also in the sigma algebra. Again, recall that a measure space is complete if every subset of a mu null set is also mu null. And it is also measurable, of course. And to establish this one, again, let us, or we need to write again this C bar as a union, one in sigma and one in n, in order to be in sigma bar. Now, I claim that C bar is in n. If C bar is in n, then we are done, because you can take A to be the empty set in the representation of an element of sigma bar. Okay, to see that a C bar is in n, okay, from star, take note that C bar is a subset of A bar. Well, this is nothing but the assumption here. A bar is equal to A union B, but B is a subset of n. Okay, and if we take, let's say, the measure of the union, of course, this is non-negative. This is in sigma bar, because A and n in, or I should say sigma, to be more precise, since A and n are in sigma. And this is less than or equal to, you apply, let's say, additivity, subadditivity, and this one here vanish since n is a null set, and a is in sigma, and we know that mu bar and mu coincides on sigma, so this is equal to mu bar a, but again using the definition and using this star last time, this is equal to mu bar a bar, but this is 0. According to this assumption here, a bar is a mu bar null set. Okay. Thus, we have written, we have seen that C bar is a subset of A union N, and A union N has a measure 0. So this is a null set in sigma, hence it is in N. Or we should be more precise. This is in sigma, and mu of A union N is 0. So that C bar is a subset of mu null set, therefore it is in N by definition of N, script N. And that proves a completeness of your extended measure space. So in the next lecture, we will discuss further properties of complete measure spaces. So see you there.